I'll be briefly discussing path integrals, uncertainty, entropy, and information, just a very basic level. Yeah, first of all, why path integrals? Like, what's the motivation behind path integrals? Now, in classical physics, we have two formulations, the Lagrangian and the Hamiltonian, and the canonical formulation of quantum physics is based on the Hamiltonian. So the primary motivation behind path integrals was, is it possible to formulate quantum mechanics using the Lagrangian? So here are some basic definitions. The Lagrangian is the difference between the kinetic and potential energies, and the classical action is the time integral of the Lagrangian from the initial time to the final time. So we look at a particle which evolves from a fixed initial state A to a fixed final state B. And in classical physics, the particle follows a unique path, which is the path with the least action. But in quantum physics, the particle can take many possible paths from A to B, and we are only allowed to ask what's the probability of each possible path. So you may ask, how can A and B be fixed points? Because in quantum physics, you cannot specify the position of the particle. Well, the target question is, if the particle is in position XA in time TA, then what's the probability that it will be in position XB in time TB? That's what we're trying to address. So we define something called the kernel or the propagator, which is the probability amplitude in this formulation. And it is, as you can see, it's the e to the I sj over h bar, where h bar is reduced Planck's constant. So we sum this over j for each possible path. So it's a sum over paths. And a is the normalizing factor. So to mathematically define the path integrals, we divide the total time interval from a to b into n time steps of equal size epsilon. And we change the summation to integration, take the limit epsilon tends to 0. Now I'm skipping all this mathematics, technical mathematics. And yeah, we integrate over all. Okay. So we integrate over all the position variables x1, x2, and up to xn minus 1. So because we leave out x0 and xn because the initial and final points are fixed. So I'm going a little fast because of the time constraint. Please ask questions if you have. So and this is the compact notation. So now let's talk about the multiplicative law of propagators. So here we can also define the kernel from A to B by introducing an intermediate point C arbitrarily. And we take the product of the kernels from A to C and from C to B and integrate over all possible values of XC. And this equation, which is the multiplicative law, in discrete basis, this is just the superposition principle in canonical quantum mechanics, which is this equation, as you can see. Now, the left-hand side is mathematically the inner product of A and B. And the physical interpretation is, if we carry out two subsequent measurements on two observables A and B, then what is the probability amplitude that we get outcomes A and B? And to get the probability, we have to take the square of the modulus. So this we can also define as the product of two inner products summed over the entire spectrum of the observable C, where C is again an intermediate observable. So we don't perform a physical measurement on C. Like in the double slit experiment with electrons, we see that if we try to determine which slit the electron went through by putting detectors in front of the slits or whatever, then we see that the interference pattern is destroyed. And because the superposition principle no longer holds in that case. Now, we have the uncertainty principle has been already discussed in this summer school, and most of you already know it. So it's basically we cannot measure both the position and the momentum along the same direction of a particle with 100% accuracy at the same time. They are canonically conjugate variables, and the product of their uncertainties is greater than or equal to a non-zero constant. So, and this uncertainty is an inherent feature of the universe. It's not because of any limitations in our measuring device. And Feynman gave an alternative statement of the uncertainty principle, which is very interesting. This is how he introduces quantum mechanics in his Feynman lectures, volume 3. So he says that any determination of the alternative taken by a process, which can take more than one alternative, destroys the interference. Now, to understand the equivalence between Heisenberg's inequality and this statement, we can look at the double slit experiment. But this time, the screen with the two slits is free to move about vertically. So if the electron is to reach the position labeled detector on the final screen, then if it chooses slit 1, it has to deflect downwards, and vice versa for slit 2. So it's possible for us to measure the recoil velocity of the screen in both the cases and find delta px. Now, if we assume Heisenberg to be right, then if we know delta px, we cannot know delta x, which means we cannot know the position of the slit. I mean, they will vary for randomly, they will vary for each throw of electron, and that means we cannot specify the positions of the minima and maxima, which means the interference pattern will be destroyed. Now let's talk about entropy. Okay, so entropy is a concept in statistical mechanics, and entropy for a system with many particles, it's the number of possible ways we can define the state of the system. So we have to take into account everything, like the number of ways the particles can arrange themselves within the available volume, then the number of ways they can distribute energy among themselves, then a number of ways they can, via collisions or whatever, they can distribute velocity. So we have to take into account spatial velocity and energy configurations when we define entropy. And of course, as we all know from the second law of thermodynamics, the entropy increases in any closed system. It cannot decrease. It will increase until the system reaches an equilibrium, when the entropy will be maximum. So in statistical physics, we define the entropy, Boltzmann's entropy. Now, this is only for systems in equilibrium. We define it as KB, L, and W, where W is the thermodynamic probability of the number of microstates for a given macrostate. And this S is the entropy of the system when it is in that particular macrostate. Like in this figure, if we say that color is a microscopic property which we cannot measure, then these are four microstates, different microstates corresponding to the same macrostate, because the macroscopically they are same. There are three balls in the left partition, only one ball in the right partition. So microstate of a system is completely specified by the position and momentum of all the particles at that given point in time. So we can think of it as a point on a position versus momentum space, which we call the phase space. However, due to the uncertainty principle, due to the uncertainty principle, it's not possible for us to know both the position and momentum accurately at the same time. So the microstate is not really a fixed point on the phase space. Rather, it's a we need to divide the phase space into elementary volumes, finite volumes called phase cell, each of volume h to the power n, where n is the physical dimension of the system and h is the Planck's constant. Now, let's consider a system which is under some external constraints. So there will be some allowed microstates, and the allowed microstates will correspond to a fixed particular volume V within the phase entire phase space, and the number of microstates, or the number of what we call the density of states, the number of phase cells, will be V divided by h to the power n. Now, if uncertainty principle were not true, just let us consider a thought experiment. Then if delta x and delta into delta px was greater than or equal to 0, I mean, if h was allowed to be 0, then g would tend to infinite from the above equation, which means if we have an infinite number of microstates, then entropy cannot increase any further. Now, this is not a rigorous argument, and I'm not saying the entropy increases because of microscopic uncertainty. That has, I think, more to do with the arrow of time. But I believe the uncertainty principle could provide a wiggle room for entropy to increase. So finally, let's talk about information. Now, in quantum mechanics, we know that mathematically the probability of a quantum system moving from state A to state B is the same as the reverse probability, which means no information is lost as the quantum system evolves, and this is called unitarity. But we don't observe time symmetry in the macroscopic world. We don't observe a broken cup pick itself up and just jump back on the table, although you observe the reverse. Because this is the concept of arrow of time, or more specifically, the thermodynamic arrow of time, which points in the direction of an increasing entropy, at least in our universe. So now, before we finally we will discuss the relation between entropy and information. But before that, what is information? Here are some very basic definitions. So information in bits associated with some event, it's I. It's called. You can define it as logarithm to the base 2 of n, where n is the number of binary questions. I mean, questions whose answer can be only in yes or no. We need to ask to completely know the answer. I mean, you cannot ask a question like, "What is your name?" because the answer to that cannot be yes or no. You can ask questions like, "Does your name start with A? Does your surname start with B?" And you have to keep on narrowing down the possibilities. And the minimum number is n. Minimum number of questions you need before you can finally know the answer. And Shannon's entropy H basically gives you a average uncertainty, the measure of an average uncertainty in information with an event where there are n possible outcomes. So here the summation is over the index I, where I runs from 1 to n. So you can think of this log base to 1 over pi. So if we assume for a moment that the probability of each outcome is p, then there has to be 1 over p number of outcomes, because 1 over p into p is 1. So you can correlate this log base to 1 over pi with this. So it's the information associated with the ith outcome. So we multiply that with the corresponding probability and sum over all possible outcomes. So this is the average uncertainty in an event, Shannon's entropy, which is very much important in communication systems as well. Now, finally, in my last slide, I will be talking about the relation between entropy and information. Now, it's slightly nuanced. It's not true that as entropy increases, the number of microstates go on increasing, and the information we need to describe the state, the system goes on increasing. That is true up to a point. But actually, the maximum entropy state or the equilibrium state, that does not change with time in its entirety. And it's also the same at all points in space. I mean, we cannot distinguish between different points in space if the system is already in equilibrium, like the idea of heat death of the universe. So we need less information to describe the maximum entropy state. So information is maximum somewhere in between as the system evolves from its lowest entropy to the highest entropy state. And this is a beautiful example of this is the entanglement entropy, or the page curve in black hole information paradox. So the entanglement entropy is very shortly I'm speaking due to time constraint. It's a measure of information of two particles which are entangled. One is inside the black hole, one is outside the black hole. And this is a very good interpretation of the black hole information paradox, since this takes into account the preservation of information as predicted by quantum mechanics. So the entanglement entropy is a measure of information. We plot it as a function of the time, the lifetime of the black hole, when it's formed and then when it evaporates away completely via Hawking radiation. So time is positively correlated with entropy. So initially the entanglement entropy or a measure of information, it increases and then it decreases. So yeah, these are the few points I wanted to discuss. And here is my conclusion. Yeah, now one important point I would like to make is that although I said that the uncertainty principle, microscopic uncertainty could provide a wiggle room for entropy to increase in the universe, but this is a very vague argument. And I'm not saying entropy increases in the universe because of quantum uncertainty. Rather, it just leaves open the possibility. But the driving force behind the increase in entropy, I think, has more to do with, as I already said, arrow of time. And yeah, so here are my references I used for this presentation. And here are my acknowledgements. And with that, I thank you for your patience.